Yes.
Okay, thanks, Martin. No, good. Thanks, Martin. So we are now at an important moment, start of a new project. This is the agenda for the kickoff of today on our eScience PointCloud project. The idea is after this opening to do a quick introduction round. So, and I think it's nice to have every person introduce himself, herself shortly, except the persons that also give already a presentation later on in the program. And I highlighted the persons that will present something with the red names. So after this introduction round, I will give an overview of the whole project. What are our goals? How do we try to achieve this? Then I hope we have Marcus Schutz from TU Vienna. I'm not sure if I've seen Marcus yet online. Not yet. Yeah, I see Marcus here online. So good, very good. So we are safe. And after Marcus, where he will show his latest visualization results of web technology interacting with point clouds. After that, Ai-Cheng Liu will give an overview of the results he obtained in his PhD research. It's nearly finished now, writing his thesis. And there are many results relevant for this project. So we are lucky in that sense. Then a short introduction by our postdoc, Vitali. He is also here in the room. And okay, I think then we have the complete setting more or less. And I think it's then nice to switch to the eScience Center. I'd like to ask them Niels Dorst. So I put Niels Dorst there because we have two Niels in the room. Also Niels, our colleague here, and who is representing Esri. Yes, Esri. After all these introductions, discuss a little bit the different roles. There's quite a number of people, but okay, who will be doing what, and in what way could we work together? Very important, in addition to say the postdoc, is also the role of the two eScience research engineers that help us with developing our solutions, and also the external experts that can contribute with their knowledge. Maybe already software solutions, data sets, feedback, wanted and unwanted feedback. They can do whatever they want. They are the experts. Then we can have an open discussion for about an hour. And before we formally close, it's good to make a summary what we are going to do next, who will be doing what and when. After that, it was planned that we would have, say, some informal drinks and snacks. But about, say, 48 minutes before the meeting, I got a message from the department that meetings could still continue during COVID time, but not with drinks and snacks afterwards. So I'm not sure what will happen if ours is cancelled in time or not. So let's see. Okay, I've made this list of participants. It was also more or less in the Outlook email invitation. And Vitali is the postdoc, so he's in the back of the room. He will give a presentation later this afternoon. Edward Verbree sitting more or less next to Vitali in the room, who is one of the founding thinkers behind the principle of point clouds as a mature representation for spatio-temporal phenomena, so avoiding conversions to gridded representations or to polyhedral or vector representations. Martijn Meijer sitting more or less next to Edward, and also online via the Zoom. He is say map generalization / database expert also in our team. Hai-Cheng Liu sitting here in the front, doing a PhD on the managing multi-dimensional point clouds, nearly finished. Myself, then we continue with the team of the eScience Center. But maybe I ask Edward to say something now. Maybe good to come to the camera that people can see you. Explain a little bit your background. Yes, visible. Yeah.
Okay. Yeah, welcome everyone over here in the audience and also there online somewhere. Yeah, indeed, I'm very pleased to be part of this project, but it's not that very difficult because I worked here for quite a long time. And as Peter told, and I think you also will show some slides in this presentation, that working with point clouds, and I always use the term the direct use of point clouds is a very nice way and a very effective way to derive more information out of this data. The more as this kind of data will become available more or less in real time and with a huge amount of data. So maybe there's no time to process those data into another kind of representation of the kind of data format. Like to use point clouds as is. And then for that I'm very pleased that this project is starting to start, and B that I think this is a very prominent topic.
Thanks, Edward. Thanks a lot. Martijn, would you like to say something to the audience here in the room via Zoom? You can see the Zoom movement of Martijn. One camera to the other camera.
Yeah, welcome everyone indeed. My name is Martijn Meijers. I work as an assistant professor here at the DRS Technology Chair with an interest in map generalization, as Peter already indicated. And we see a large uptake in point clouds being collected coming from laser scanning, coming from photogrammetry, really from all kinds of different sources, even from space. So making them available within the GIS world is something that many people are working on, and I hope that this project will make a contribution to that, so that we can really use this incredible amount of useful information in all kinds of applications, sharing them and also making them usable, maybe even stored at a remote end somewhere in a cloud environment, and then making them possible to pull the relevant points in your application. So I'm very pleased to see you all, and let's see where we can bring this together.
Thanks, Martijn. Okay, next person on our list was Michael Kreutzer, head of department. I'm not sure if he's here. I've not seen him in the list. No. And he promised also to be there at 4 o'clock, not at this moment. So, okay, let's then continue with the eScience Center. Okay, Niels will present something on behalf of the eScience Center later on. So maybe Thijs van Langveld, can you present yourself?
Yeah, sure. Name is Thijs van Langveld. I'm a research software engineer at the eScience Center. And my background, I come from point cloud surface reconstruction. So I did my PhD at Utrecht University on reconstructing urban surfaces from LiDAR scans, and then continue that onto reconstructing cultural heritage objects, also from smaller scale LiDAR devices, into 3D reconstruction from panoramic images at Cyclomedia. And then at some point I also arrived at the eScience Center to kind of continue on computational geometry based challenges. So I'll be the lead engineer on the eScience Center side. but I'll also be representing our team there, Team CAT, and I'll give a very short presentation at some point, hopefully, to introduce the other members of the team that will kind of share the development load from the Science Center's side.
Okay, thank you very much. Meindert?
Yes, I'm Meijert Grotes. I'm also an EI science research engineer at the center. And the reason I'm joining today is because I've kind of been the lead engineer on a project looking into using the AHN3 LiDAR data sets in the context of macroecology and doing feature extraction from massive LiDAR point clouds. So yeah, it seems sensible to spread the knowledge of what this project is doing in the center via people who have experience with the field, and B, also to see whether there's anything that we can contribute in some way. Of course, supporting Thijs if and as he needs it.
Meindert, thanks very much. Francesco?
Hi, I'm Francesco Martino. I'm also a research software engineer at the eScience Center. I joined this meeting basically for the same reasons as Meijert, so I joined in this project working on point clouds, basically in particular on this AHN data set. So I'm happy to contribute and whenever possible, and to also learn from this project, so to have some knowledge exchange. And yeah.
Thank you, Francesco. Welcome. Adam?
Yes, good afternoon. Yeah, my name is Adam Bloom. I'm one of the tech leads. Actually, today I will be representing the tech leads of the eScience Center. So the role of the tech leads is to be able to act as a technology advisor for the research project at the eScience Center. So we will try to follow the project, and hopefully we give some good and useful contributions to the project. My background is in computer science. I've been doing research at the University of Amsterdam, and I'm still having half-time position at the University of Amsterdam in terms of a distributed system, building software for high data intensive applications on cloud, grid, etc.
Okay, Adam, thank you very much. And then we go back to the room, to the people from Deltares. First, Fedor.
Yeah, hi. I'm Fedor Baert. I work at Deltares as a specialist of the data science and future modeling. Well, at Deltares, we are a research institute for the open source, and we have interest in many point cloud developments, local maps of the coastlines in the world, reservoirs in the world, and we want all the angles where new point clouds. So focusing very detailed in local field measurements and in our own lab on local. We have a lot of interesting applications. See progress.
Thanks, Fedor. Martin, a colleague.
Hi all, I'm Martin Konk. I also work at Deltares as a researcher. My main interest is in using point clouds, actually LiDAR point clouds from space, in elevation modeling around the whole world. And it's also been the topic of my external PhD that I just started here.
Very good. And the reason why Deltares is involved, that okay, the project is about developing technology to better support point clouds. But to prove that, is it working, is it not working, we want to apply it. In the project proposal, we discussed that we have this domain of, say, water management or hydrology, where we will try to apply the new technologies that we developed. Okay, now we go back online again to Marco Schutz from Vienna. Marcus, are you there?
Hey, yes, I'm there. So yeah, Marcus Schütz from TÜ. I'm doing point cloud rendering research about rendering point clouds in web browser, rendering them in virtual reality in real time. And yeah, I'm very interested in this kind of project and what kind of collaborations there might come out of it.
Marcus, very welcome. Marcus is the as you can also see from the email, the key person or the main developer of the Poetry visualization software from his PhD research in Vienna. Okay, now we move to the next slide, and this is maybe also a little bit of a switch. This slide contains, say, the experts that are, say, surrounding our project and give us, say, feedback, advice. Marcus was perhaps on the boundary. He is kind of in the project proposal, but he is far away. But let's now go to the people really far away. First, Mike Horemmer from Oracle. Yeah, Mike, you're muted.
Can you hear me?
Yeah, now it's better.
All right. So I'm Mike Horemmer. I work at Oracle in Oracle Spatial, and I work on point clouds, 3D, coordinate reference system support, and yeah, that's it.
Okay, and it's good to know that in the previous point cloud project, we have worked a lot together with Oracle, doing a lot of testing, benchmarking, different storage solutions, individual points, blocks, all kinds of queries, and infinite number of benchmarks. Really. And it's something that you can really do the rest of your life, but it's not the purpose in itself. But it's good to see and compare two different solutions. Then the colleague from Mike in the Netherlands, Shintaro. Yeah.
Hi, Peter. Hope you can hear me. Yes, Shintaro Nagaoka, working at the Oracle in the Netherlands. A couple of years ago, I was privileged, very, very fortunate to be a part of the previous project led by Peter. I'm not the real specialist in this area and no engineer, so I have to figure out how I can think of some added value for this round. Thank you.
Thanks, Shintaro. Yeah, very important and also very useful to have this, say, opinion and vision from somebody who's out there in the real world where the customers with a lot of data are. I'm not sure if Stefan Willems is there.
Yes.
Yeah, okay, Stefan, please go ahead.
Yes, my name is Stefan Willems. I'm a cloud engineer at Oracle Cloud Infrastructure. So I'm also here to participate in this session because based on our product line that we have for high performance compute, GPU, and of course Oracle database, but also non-Oracle database that we can run in Oracle Cloud Infrastructure. So I'm the representative from Oracle from the cloud side.
Okay, Stefan, very welcome. Then we move to Martin Kodde, Delta, who could not be here. But I think Stijn is here. Yeah, please, Stijn.
I'm Stijn from Delta. So we also do a lot of work with point clouds, for example, the AHN quality control, which is direct data set. We're also busy with making a web environment to visualize those data point clouds, for example, the AHN. And also, looking for other point clouds to visualize, for example, information, which this can be very interesting.
Thanks, Stijn. The another person not present here, then also without a representative, is Bart Beers from Cyclomedia, producing also a lot of point clouds in addition. Imagery, he will be in the expert team. He wants to be in the expert team, but he could not be here. Then here and in the room is Niels van der Vaart from Esri, also a very well-known company.
Good morning, or good afternoon, everyone. My name is Niels van der Vaart. I'm with Esri, but I'm also privileged to have a zero-hour contact with the department here, so we connected to the research here. At Esri, I've been doing a lot of things related to treaty over the last decade or so, and now I'm in the Netherlands also. Related to point clouds, we see a couple of things. So first off, we are investing a lot of time in making standards distributing point clouds over the web. That's an effort Esri is investing in visualization and also using point cloud for deep learning applications is something we're doing. And on the other hand, I think I can also chip in some of the experiences from the user community. because we serve a lot of people which also have their own ideas what they want to do.
Very good news, thanks. Now we move back online again to Jeroen Leusink from het Waterschapshuis. Het Waterschapshuis is kind of the owner of the AHN data together with Rijkswaterstaat, and which is one of the key data sets. Jeroen?
Yeah, good afternoon. I'm Jeroen Leusink from het Waterschapshuis, indeed. So I'm the technical manager for the AHN and imagery program in the Netherlands. And I used to be working at Aerodata, where I was team lead for the LiDAR department. So I know both sides of the contract. So
yeah, the production and the user side are very good. Very important to have the experience. Welcome, Jeroen.
Another remark, it's very hard to understand people who are introducing themselves when they're not behind the desks online, at least.
Okay, maybe they should move closer to the camera. I think we are now nearly finished with the loop, but okay, Jeroen, sorry for that.
No
let's see if we can, no, I don't think we have any more people on the list that will introduce themselves, but the presenters for sure will be here behind the desk. Then we go to the Forte-EU research data. So Forte-EU is the collaboration of the 4 technical universities, Delft, Eindhoven, Wageningen and Enschede. And they try to support the different universities and their researchers. And also they had a role in the previous project. And Adi Nohebel, Adi, are you here?
No, Ardi couldn't make
okay,
it.
Ardi isn't here, but Ardi's colleague Roel is here. Roel, please go ahead.
Yeah, so hi, I'm a software developer at Forte Research Data. My colleague was involved in the previous part of this project, but I wasn't. But nevertheless, I'm interested in learning the challenges of this point cloud. It looks like very promising technology, and Forte Research Data does long-term preservation of data. So I'm trying to figure out whether we can be of any help in this project.
Okay, Roel, welcome. And last but not least, we go to China and to Xifeng Guang.
Hello, everyone, and I'm Xifeng Guang from Wuhan University, and my research focuses on the big data storage in open source databases such as HBase. And 5 years ago, I stayed in QDepth for 1 year. It is a very great experience. And in that year, I worked with Professor Peter on nD-PointCloud management. It is very interesting. So, okay, yeah, nice to meet you all. Yeah.
Thank you, Xifeng. Thank you.
Yeah.
Okay, I think we covered the introduction, except the persons who will present. And yeah, to be sure we are all on the same page, I thought, okay, I start with the overall project presentation. You've heard me already a lot, but sorry for that. But you will hear me a little bit more, and then it will start to get a bit more quiet. So let's switch to the presentation with the project overview. Yeah, this is really teamwork and not starting now, starting already decades ago. And yeah, we had the previous project, which I will tell you a little bit about, but also in between. Many students, master students, PhD students worked on this topic under the supervision of Edward Martijn, myself, and also Haicheng, the US, done a lot of work, and now Vitaly has joined us since 2 weeks, more or less. You are here in the beautiful building of the Faculty of Architecture and the Built Environment. We are there in the section Digital Technologies. And yeah, that is our home from which we work. This was the previous project, also an e-science project on massive point clouds. We did a lot with data management, compared different databases, SQL, non-SQL databases, Also file storage solutions for point clouds, especially loss tools, of course. And also we developed web viewer and a tool for downloads and doing online analysis, simple analysis. And these were the partners back then, more or less the same. So Fugro has become GeoDelta because Martin Koldem moved. I wanted to have Martin in the team. 3DU has become 4DU. And Rijkswaterstaat has become het Waterschapshuis. There's a lot of stability, and I believe in stability to make good progress. So this is what I want to tell you in the project overview. First, some project details, how the project was set up, organized. Then this vision of direct use of point clouds, let's say Edward's vision. Then something about this infrastructure to serve the society with large volumes of point cloud data and also operations on it. Then going to the foundation of that is the concept of the multi-dimensional point cloud. So not per se 3D, but could also be 4D, 5D, or 6D, or 10D, if you think that's useful. Then one thing we have to be really focusing on is the volume of data. Point clouds usually get quite large. How can we address that? And in the end of this introduction, a short conclusion, very short conclusion, I promise you. So this is a new project, will be running for 3 years, started 2 weeks ago. The eScience Center will contribute with 2.5 person year. Deltares with the proof of principle in the water management application. In total, the project budget is this amount of money, €500,000, but basically there is no money, there is only staff. And we have equipment from our own resources. We will use a software stack, starting with the databases. Different options are open and on the table. And also visualization software and other tools, of course. And Poetry has a very important role in the visualization. This is the core team as presented in the project proposal. And now with the name of the postdoc filled in, Vitali, he will be the only person that will be working for 3 years for 100% of his time on the project. The others will do it part of their time, but Vitali is the key person, I would say. Okay, we organized the project in a number of modules or work packages. The first work package is about communication, like what we are doing now, organization, also dissemination, writing publications or going to events and explaining about our results. The second work package is about the conceptual model or the theoretic foundation. That will be done in 2 iterations. We'll make a first attempt as good as we can, and then we're gonna implement it, apply it to an application, and we try to learn from it. We hope to be able to do a final refinement of the approach of the model, the theoretical model. Maybe it can be improved. Okay, the model is implemented in work package 3, data management aspects, the storage, the retrieval, the structuring, all these kind of massive operations are conducted in a data management environment. Work package 4 is about more computation, and it can be all types of computation. Flow computation over point clouds, line of sight computations, change detections, coordinate transformations from one reference system to another reference system, and all these things are quite heavy operations. And so we need high performance computing and high throughput computing to push through this volume of data. And in the end, we want to see it, we want to work with it, we want to interactively query it, and there is the visualization. That's not the end. That's the visualization part. The end is the proof of principle where you use it in an application. That starts already early to kind of decide on a specific application, specific data sets, what are the requirements from the user side or the using side, and then take that into account in the other work packages. The way of working is, as the Science Center is being practicing in other projects via sprints. That is very short periods where, say, a small team works together very intensively and collaborates to reach a clear predefined goal. And that's alternated with periods, say, where there is a refinements of the things developed during the sprint, say, more good, like the part at the bottom. Yeah, documentation, and make sure everything is yeah, also more bug-free, robust. But this is the relationship between the different work packages. A small iteration is at the end. We want to improve the theoretic foundation of the point cloud model. So this is exactly the same as what was on the previous slides. Important to mention is maybe also standardization. So if we want to share point clouds on the web, we have to agree. The server and the client have to talk the same language, the same protocol, the same encoding. And there are many, many different encodings of point clouds. I think at least over 100 encodings exist, and maybe even more, 200, I would not be surprised. Some more often used. It is more than just data encoding. It is also the protocol between the server and the client. Okay, then this this vision on which the project is founded, and that is direct using the point clouds, and not only for visualization, also for analysis, simulation, and other types of computation, and not converted to other representations to get polyhedral models or gridded models. So direct use it. The idea is, okay, it can be faster. After acquiring the data set, you can use it without converting it. There is no data loss. If you go to a grid or to polyhedral representation, vector representation, you will lose some data, and the data may be important, depending on the application. But because the representation is more accurate, the results of the analysis should be better. We should have better results, better flow computations, better line of sight computations of view sheds, better routing, whatever is your purpose. We think it is rather easy to support continuous levels of detail or continuous levels of importance. It is very hard in gridded representations. Okay, you can change the size of a grid cell or a voxel by a factor 2 in every dimension, but these are kind of discrete steps you then make in your imagery or voxel or data cube. For vector data, it's also rather hard to maintain the topology structure if you have, say, a varioscale map. And for some applications, point clouds are by far the most realistic representation. So think of, say, how to represent vegetation, trees, bushes, things like that. Yeah, if you've seen the voxel images, they have to go to incredible fine voxels to make sure you see the leaves on the tree. And if you have a polyhedral representation, you have to do it with, say, an in-between complex polyhedron with then texture on top of it, some images. Still, that will look not that realistic as the point cloud, is my impression. And that helps also in analysis and computation. So if you do view shed computation with vegetation based on a real point cloud, that result should be better, more realistic than one with a grid or one with a vector model. Okay, it's not only benefits, there are some drawbacks. And one drawback is a lot of data. So we have to organize the data well in order to be able to use all these benefits. And the second thing is people have invested decades and decades of programming and coding, and putting the laws of physics into software code to do their computations. And we have to rethink that. How can we change the existing algorithms for routing, for flow computations, when we change from a grid to a point cloud, or from a polyhedral model to a point cloud? Most likely, it will be existing next to the two other main representations with conversions. And so I see the future where we have three important representations of spatial temporal things with conversions in between, where my expectation is that the point clouds will be the most often used ones, so the most important ones. To give you an impression of what type of analysis you could do directly on point clouds, and what our students have been doing is, for example, solar energy potential computations, solar envelopes. Okay, what is the shadow that's being casted by buildings or other objects? 3D routing, indoor, outdoor with point cloud models, view shed, line of sight computations, change detections or deformations, volume analysis, vegetation analysis, and the CLOD, or the continuous level of detail, not only for the analysis, for visualization, also analysis. So this routing is in the Bouwpub, which is next to this building on the parking lot. And that is for bringing a beer. If you are in one place of the Bouwpub and the drone is bringing your beer, and then this 3D route is computed on the point cloud. View shed done by Granting, who was visiting our university 3 years ago, 4 years ago, doing visual analysis of the environment. She worked with Edward on doing line of sight computations directly on the point clouds, on the AHN data. Some students, a group of students, worked in their synthesis project on change detection, AN2, AN3. So say 5 years later, and see what has changed. And again, the scene around our building, is always nice to look at things you are familiar with. What has changed? You see a lot of green. I'm not sure if you can see my mouse. Yeah, you can see my mouse. So this is a new building, student home. The serres of our building were made new. Some trees were taken down. Okay, that happens. Of course, there are always changes. There are also not changes, because it's sampling, and you are never sampling at exactly the same location. So that's not a real change. Other things change gradually, like trees. Vegetation is growing. It's also a good way to monitor the healthiness of these objects. Coastal monitoring, more close to the domain of Deltares. 2 examples. These are 2 images that compare 2 moments in time. The upper left image is 1 hour time difference, and say the bright right and the bright blue is 1 meter up or 1 meter down. So in 1 hour on the beach over there, the sand was moved quite a lot. This was the Chiara storm. And the other part is so 1 year of the new Onsbosse zeewering, not the dike, but the new dunes there, and how are they developing over time. And today, a lot of this is done and analyzes with de-reefed grids, and this was an example by a master student this year in Schneider, doing it directly with point clouds. Last example, flow computation of stream delineation on AHN data. And this was compared to the official stream by a water board. In green is the computed stream, and in blue is the official stream as the water board defined that stream. And yeah, you probably can argue what is the true location of the stream. But the results are very promising. And yeah, this is really a set of examples where you say, okay, yeah, point clouds are really very useful. You can do a lot of things with them better than you can do with the other representations. So we want to develop a good foundation for that, and that is the multi-dimensional point cloud representation. Actually, it's not only for geographic applications or hydrology or water management, but everywhere where there is something spatial and temporal or multidimensional in medical applications, physics, astronomy, architecture, archaeology, gaming, and so on. We want to support point clouds in the whole processing chain, from acquiring the data to using the data, and everything in between is an important role for the data management, but also the computations direct on point cloud. And we believe in something important, which is the deep integration of space and time and scale, and maybe even other attributes. And that will help us in more efficient storage, more compact, faster selections, giving you what you need, and also providing more functionality. For example, a smooth zoom or a perspective view or better analysis. Due to the deep integration of space, time, and scale. It can be big data, and it's seldom small data. Sometimes it's okay data, but not too big usable. So there have been data sets reported up to 35 trillion points, so really a huge amount of data, both in astronomy and geoinfo. And yeah, for that, to manage that, we need some kind of infrastructure. And there are many organizations, professional, and in the future also probably citizens that will be producing point clouds. And that are willing to share that. That sharing must be, say, facilitated by some kind of solution. And I have a big respect for what the people in the OpenStreetMap community did. And so they were able to compete to what, say, the national mapping agencies did for many decades or even centuries. And they really do outperform them in, say, actuality, being more up to date with OpenStreetMap than what is, say, the official topographic maps of a country look like. And that is basically often vector data and 2D data. So can we do something similar with point cloud data, knowing that the volumes are higher? So what we could do in our prototype and our pilot is select some countries that have large volumes of point cloud data publicly available, like the Netherlands, but also UK, Denmark, USA. And for example, in the United States, they have this program, 3D-EP, so the 3D environmental program. And already today, they are also laser scanning the complete country. They have this 35 trillion points, and it's not yet completed, and they want to do it continuously. So when they're finished, they want to update it. Of course, the USA is a much bigger country than the Netherlands, and so they have to think about, okay, at what detail do they scan the country? Probably cities more detailed than, say, very, say, remote areas. So that is about, say, the domain or the area, and maybe you could also use say, satellite-based laser measurements, so ISAT-2, or the device mounted to the space station, also having a laser scan. We could do time series with and we already have more or less 4 good time series. It's not so high frequent, but still, Deltares has more high frequent scans of the coast. We could also add different types of data sets, for example, from a municipality of higher resolution, or maybe even from a citizen that is making an own scan, and that is somehow fitted in. And this fitting or registration is a very hard problem. It is, people of GeoDelta know that. That's their job to make sure it's done well for the national data set. So can you imagine if this data set is coming in from all kinds of directions? We can integrate both the on land and the point clouds in the marine environment, say the sea floors, ocean floors, and typically then it's not laser scanning, but multi-beam echoes. There could be other techniques from imagery, the reef via dense matching also. What we want to have as a functionality is to put on and off certain point cloud layers and play with the styling, compare point clouds between different years or different scans, do animations, see what has been changing. Be also scalable, so if we get more data, make sure that we can process that. And store somehow that not in separate files everywhere, but in the database management system. So this is a sketch of this architecture. Let's say on the right side you have the client using his own device. Could be a mobile phone, could be a computer, could be a tablet, and he's connecting to the portal of the OpenPointCloud map server. And then depending on the request, connecting to the data stores or to the processing nodes that help to give the client the wanted results, a data set or a simulation or a visualization environment. Okay, what do we have? Okay, we have our hardware, so a number of computers we today use and we can still use and use in a different way in the future. So GDMC.nl, especially for dissemination, events, papers, the AN, PointCloud.nl site. We probably should upload AN3 and AN4, maybe other data sets to play a node. We use the PO3 for the client side for viewing. We have a number of other domains which are relevant. nD-PC.org is nice, also internationally. Yeah, the software stack has been mentioned before. So what about the data? When I think about point clouds, I always think first of AHN. This fantastic data set that we have here in the Netherlands already for quite a long time. And is available open to everybody in and outside the Netherlands, so great for testing. Another data set could be via cyclomedia. They also have laser scanning and imagery, and they really drive all the roads in the Netherlands and in other countries. And I think they have estimated that the data set for the Netherlands would be about more than 50 trillion points, which is small words, but a lot of data. And I also visited the website of the 3D elevation program of USGS, and today, or yesterday, it was actually day after this, 34 trillion points. We also did buy an iPad, not to play with or to do. I don't know what you do with an iPad. But it has a laser scanner. That was the reason why we did buy the iPad. And that shows that in the future, instead of taking pictures or doing videos with your mobile phone or with your tablet, you will be making 3D pictures or 3D videos. And these are together with some software, more at the consumer level. But don't underestimate the consumer. We have so many of them. Together they can do really a lot of data acquisition. And for more, say, professional laser scanning, we could say work together with some of the partner companies, say Leica in the Netherlands. Our colleagues here at Civil Engineering have a ZEP Revo. Our main machine for benchmarking was and is still this HP machine. This 616 cores, 128 gigabyte main memory, 80 or 100 terabyte of storage, which is nice to play with. In the past, in the previous project, we also worked with Oracle Exadata, which is a piece of hardware specifically for data management. You could call this the counterpart of the GPU, but then for data management. And so hardware indexing, and not by software. So very fast. And maybe depending on what we think of together, we could do something similar in this project again. Another very nice option is the new Delft high performance computer that is now being put together, called Delft Blue. It is computer number 250 in the world ranking of the top 500 of supercomputers. It is not yet available for the researchers of TU Delft, but it will be soon, within 2 months. In January, it's available. It's actually based on Fujitsu's hardware. And the key person in Delft is Professor Kees Fuik from numerical analysis. It has 400 nodes, computing nodes, and you can choose out of 3 types. Say for computation intensive, so you get a lot of CPUs. For memory intensive, you get a lot of main memory, max 1.5 terabyte main memory, or say massive parallel, and then you can get a node with many GPUs, NVIDIA Teslas. And it has a good storage system attached to it. And our faculty has so every faculty has a use right. So we have 6% use right, which does not sound a lot, but okay, it's a big machine. And then we can use it for a day or for a week. Say 10%, probably can do quite some nice computing, like structuring the point cloud or doing change detection or flow computation or all these things you wanted to do. Okay, then this theoretic foundation and the point cloud. So 3D for space, yeah, X, Y, Z. But okay, it's changing over time. So we have time as a dimension. So it's a 4th dimension. Then we have levels of detail or scale or levels of importance. So that's the 5th dimension. And so it's easy to mention 4 or 5 dimensional data sets. And what I mean is that these dimensions are used to organize the data, because that's how we use the data, how we retrieve the data. There could be other dimensions. And so if you model flow of water, it could also be the direction of flow, the speed of flow. You have say 3 other dimensions added. And actually, Hacheng will show you what he did with that, I think 8-dimensional modeling and retrieving. So a lot of data, how do you organize it? Yeah, probably the best thing is to put it in blocks, to containers where you have coherent sets of data. And this is quite familiar with what people do in raster data. They build a kind of data pyramid. And this data pyramid is at the bottom. Here you have basically the most detailed data covering the whole domain, whole country. At the higher level, you have less data, still covering the whole country, let's say less dense. And at the top level, you have the most coarse representation, still covering the whole country. So, say spatially, all the levels cover the whole country. Storage-wise, at the more abstract level you go, the less data it is. Therefore, it's a pyramid. So you can use this, for example, if you're making a viewer, you're standing on a certain location, you view in a certain direction. Okay, nearby you can see more. So you want to see more detailed data. So you get the small blocks with a lot of data. And medium distance, you get the medium-sized blocks with say medium density. And far away, you get the big blocks with a big area, but say, rather sparse data. And yeah, there are a number of drawbacks. The biggest drawback, I think, is that you have a discrete number of levels, and that will show in the use. Another small disadvantage is that you have to create a structure. Usually it's an octree, it's about 3D data. Doable, but still you have to do it. So this is an example is the previous viewer we developed with PO3, and this was AN2 with 0.6 trillion points. But you see the blocks. You can hide the blocks by making the points a little bit fatter, but that's cheating. Actually, We've shown probably too much here and too, yeah, not enough at the other side of this block boundary. So it is not what you want. Okay, after that project, I was really unhappy about this after the previous project, and we were thinking, okay, how could we resolve this? We had a master student working on the project, Jeppe van der Made, and said, okay, when these are the blocks, and this is what I want to view, maybe I can shave off these density jumps from data density. And so he shipped the blocks to the client, and then he did this kind of technique. You have a view position, you look in some direction, and depending on the distance to the viewer, a point gets a radius. And the smaller the distance, the smaller the radius. And if another point is already overlapping with you, you cannot be added in the view as a new point. And so one by one, the points are added to the scene. And so in this way, you get a gradual transition. We discovered that you had to overfetch, say, a lot of data, nearly a factor of 10, to be able to make a smooth view where you could not see the density boundaries anymore. So that is fetching a lot of data over the web to get a nice view. Another solution was worked on by Marcus. He was not working on his poetry viewer, but on a virtual reality solution. So he had, say, nearly 100 million points in the memory loaded of the GPU. It was an indoor scene. And on the left hand, you see again this, what you normally would get with discrete levels. High is high density, a lot of data. Green is low density data. You see the boundaries when you make the transitions. And and it's too much to render 100 million points. So left and right, 90 frames per second. Even a good GPU cannot do that. And so you have to select points, and Marcus can tell more about it later. So what he did is he selected points based on the center of the view, the distance to the viewer, and that it was also gradually reduced. And then selected, you cannot read it anymore. I think about, you can read it, 5 million points. And these can be rendered very quickly. And then every 10 frames or so, he is checking, okay, do I still render the right points, or has the user moved? So should new points be added to the scene? Okay, it's also kind of post-processing because the data was already at the client side. And we were thinking, could that not be different? Parallel to this point cloud work, we're also doing a lot of work with vario scale maps, normal vector maps. And we came up with a solution where we use an additional dimension to represent changes over scale. And so adding a dimension to an object was the solution. So if we could add a continuous dimension, so a 3D point would become a 4D point. And the fourth dimension is the scale or the importance value. And if we do not make that fourth dimension, say, a discrete value, but kind of continuous value, and then we can select very smooth. We can use both X, Y, Z and the importance value in the organization of the data, say in the clustering and in the selection. But okay, how to create a good continuous level of data distribution or continuous level of detail distribution. So somehow I had in mind it should be similar to this data pyramid that is used in raster data, that is also used in the current poetry viewer or octrees, but without the discrete levels. And for quite a number of years, I had no clue. I really had no clue how to do this. What was a nice transition? And actually 2 years ago, I came up with a solution. And as you will see, it is super simple. So this is the data pyramid, but okay, now a bit tilted again. So I have, say, 4 levels. And the bottom level has the most data, the level above has half of the data, the level above has half of the data, and the top level has half again. So it's half, a quarter, an eighth, and a 16th of the data set. And you can share the amount of data the levels have in comparison to the total. Okay, but this is discrete, so I did not gain anything. And this is one-dimensional, factor 2, but you can also do it 2-dimensional or 3-dimensional or 4-dimensional. Okay, and this is the solution. I split the levels into half levels, and I apply the same function. And so this column, the number of points I can store in a level, is the function 2 to the power level, 2 to the power L. So here L was integral, 0, 1, 2, 3. So 1, 2, 4, 8 is the number of points. I had to do exactly the same, 2 to the power L, but I have 0, half, 1, 1.5, 2. And okay, I get 1 square root 2 as a number of points I can store. Okay, these are not individual points, but say groups of blocks of points. And the funny thing is, if you then compute the percentage that the half levels have, and of course they add up to 100% again, that's not a surprise. But when you add up a pair, at the bottom half and the top half, it is exactly the old value again. For example, the 2.8 and the 3.9% of the two first top levels is together 6.7. And that's the same 6.7 I had before. So that means I keep the behavior of the data pyramids, which is nice for zooming and perspective views and computation. Okay, I can do it once, I can do it again. And I get these values, and the same properties hold. And by coincidence, my son was studying mathematics at university, and I asked, okay, yeah, I have the feeling there can be an elegant solution, and he derived the probability functions for me that go not into discrete number of refinements, but an infinite number of refinements. So mathematicians have no problems with infinite. They can have formulas for that. And I have now a probability function, a commutative probability function. And with this function, I can do a computation of an assignment, a random assignment of a level, a continuous level to a point, having kind of the same properties as the data pyramid has. Did it work? Okay, this was the mathematics. So we tested the formulas. Yeah, they look kind of proper, the same as I had with my hand drawings. And it's a lot of work to put them in PowerPoint, but okay, this MATLAB function of my son worked much better. Okay, then it was time for using it. So this was the idea. I'm standing here, I'm viewing in a certain direction in the PointCloud data cube. At the bottom nearby is a lot of detail, and nearby I want to see that. And so in blue is what I want to select. So nearby I want to select everything from unimportant to important. Far away only the important points, and that gradually changing. Okay, this is what Haicheng implemented, and a bit similar to what Marcus color coded. So the color is now the density, the local density of the number of points. And you see it's a gradual transition. So it does work, and also credits to Xue Feng and his team in Wuhan. Also made the web viewer on this principle. So this is now a third person's view of the guy standing there down there, but I moved away from that. And you can also see the data blocks, which is used to store the points to be shipped to the client. Okay, this is a cool thing of one of the master students very recently. Make sure you can see it. So actually it was in the beginning of the Corona time, Liao Zhang was planning to do a virtual reality point cloud project. We have nice equipment in the VR lab. And what happened? She traveled to China for the New Year festival, and she could not travel back. And that was after making the plan for the master thesis. And yeah, I cannot travel back. Oh, that's a problem. Yeah, we have to think of doing a little bit different, not too different. And we came up with a solution. Okay, do you have a mobile phone, smartphone? Yes. Okay, let's do augmented reality instead of virtual reality. Yeah, augmented reality is even more cool than virtual reality. It's in the real world. But there are challenges. The amount of point cloud data and the memory of the CPU and the GPU on the mobile is given attention. And you still want to have good quality in the rendering. So she used R-Core and the Unity game engine and developed really a nice environment. You also did it with AHN. So you could put AHN on the table and look around and walk around and see. And it stays on the same place. You can zoom in, zoom out. And what happens? The same trick as Marcus did. Every X frames, we reassess, are we rendering the right points? If we walk closer to the points, we get more points there. But you can skip other points that are now not in view anymore. You can, you can walk around it and you can do anything. It stays in the same place in your room. Okay, many applications. Outdoor for architecture. See if you can put there a new building in a point cloud model. Indoor, as shown, you can put new chairs, other chairs there. But also outdoor, I think, change detection. And so if with the computation, you see there's a big change in the location of a dike, then you could go there and then the point clouds could be superimposed on the reality and highlight where the computed changes. Maybe it's an artifact of the sensing, maybe it's an artifact of the processing, but maybe it's something with the dike itself. And when you're there, you can check. So really nice to do. It's big data. So we want to store this data and basically in some kind of database management system. And what we have is multidimensional 3D, 4D, 6D, 8D data points. So how can we store it in the memory of a computer that is basically a one-dimensional address? So that's a mapping via a space filling curve. So that goes from nD to 1D. So here you see an example with two curves, the Morton and the Hilbert curve, very often used. And this mapping is two directions. You can map from a location to a position on the curve, or from a position on the curve, you can go back to the location in the 2D or in the 3D or in nD space. Okay, we can use this to organize the data, and the data is organized with all dimensions because they are kind of used together, these dimensions. Note, it's also kind of quadrant recursive or octant recursive, similar to Potteries octrees. So that's same property, kind of divide and conquer. My preferred technique is to use an indexed organized table on the space filling curve value. So a point is an nD point is becoming a key, space filling curve key value. And sort on that key value, then I sort all my data in nD space, basically. That's what's happening. And I can also retrieve it. If I do full resolution keys, meaning using all the details from the X, the Y, Z, the time, and so on, I can also decode it. So that means I don't have to store X, I, and Z separate. I only have to store the key. Then I know everything. The key is everything. So the key is used for clustering, indexing, but also for the data. And an index organized table is a way to combine the data and the index. Okay, what we need to do is when we have a query, for example, a polygon or a circle or a view frustum, is to rewrite that geometry into a number of ranges on the curve. And yeah, there are many challenges. What database to use, how to distribute the nodes of the database. There are many curves, Morton curves, Hilbert curves, okay. maybe you have many properties or attributes, but what do we use in the organizing dimensions? For example, if I have AHN data, I would probably, and continuous level of information or detail, I would probably put the X, the Y, and the CLOI, or the continuous level of detail in the key, and not the Z. Because the Z is not selective in my queries. I select a location and a scale, and that's on, that's also how I want to sort the data. And so the way I want to ask is also the way I have to sort the data. So if I ask never in my selection condition something related to Z, it has no use to put it in the key, in the organization, in the data organization. But if it's not about AN, but say a point cloud model of a big building with 10 floors, then the Z is selective, and probably then it would be good to include Z. Okay. Instead of storing it individual points, you probably it's wise to put them in blocks, do compression, and do things in parallel. Overall scheme. This is the big scheme. So we have from the sensor, the point cloud coming in. We add CLOI. We compute the space fill and curve key, and we store it in the database. Ready. Now we want to do a query. What we then do is, okay, we, from the query geometry, the selection area, we compute which parts of the curve are covered. That's what we call the ranges on the curve. And store that in the table, temporary table with these ranges. And then we do a join. And then we get quite precise the overlap of our query geometry. If we want to have the exact output, then we would have to do the second filter with the exact geometry. That means also decoding the key into a point and doing point and polygon test, or things like that. Okay, this is an example. If I have a polygon as a query geometry, then the Morton ranges would be these values if I refine to a certain level. So in this big area below, and so I split into 4 parts in a quadrant, and this is 0, this is 1, it will be 2, and this will be area 3. So I'm happy, this is completely covered. So this is quad code 1, and means the Morton range from 0 to 15. These are 15 cells actually. I do the same for the parts in the northwest, but only 2 medium-sized cells are completely covered, 10 and 12. These result in smaller ranges, and I have a little part in the 4th quadrant, smallest level 300, and that's actually a single Morton value. So these are my queries. So if I want to do a query, I do just select my points where the point is inside this range. And these are real values, so real data. And this gives me then overlap queries like this or this or that. That is how we did it before. So an example with a circle and this queries and selection areas. And what you can do is combine neighbors. So note that the range from 0 to 15 is a direct neighbor from 16 to 19. So instead of having 2 ranges, I can make 1 range from 0 to 19 and adding nothing, adding no space. So if I do that, then you get the second image, and that means it are not all squares or cubes anymore, but say funny shapes. But these are ranges on the curve, consecutive ranges, without adding space. So I get down from 176 cells to 32 cells to approximate the circle content. And I can go down and down and down, say requiring less ranges, 30 ranges, 20 ranges. But then I add more space outside, because if I then merge ranges, then I also include some space outside, which was, I want to be sure I always give data which is inside my query region, and maybe also giving data which is outside. And therefore, the red areas are added to generate fewer ranges, but larger ranges. This was done by Stella, actually at Deltaris Fedor, quite some years ago. Then the question arises, are there any drawbacks of putting all these dimensions in a key, in a single value? Yes, there are drawbacks. First of all, if you have full resolution keys, you have a lot of bits. And what data types can you use to store all these bits? There are options. You can use varchars to character encode the bits. Cost also some overhead. You could use Oracle number, which you can also probably store quite high resolution, say 6 to 8 dimensions without any resolution of data or accuracy. But it's an issue. There is a limit. And also, yeah, you have to rethink, do I use all the dimensions when I'm querying or selecting? And for example, in AAN, there's a surface here. So this is the Earth surface. I do a query just on the location XY. So I give the polygon of the municipality of Delft. So that's, or a box. So I just give the XI dimension. What means in the Z, it becomes a prism. That's what I ask if I don't specify the Z. So if I specify upper lower boundary, then I get a block. If I don't specify it, I get an infinite prism. That means my query geometry has a lot of boundary here and down there where I have no data. Okay, and that's wasting, generating boundaries, costing time. Okay, to conclude, and to give others the floor, I think what we have in the proposal will become a reality already because we worked on it in thesis projects of the students. But with the help of the eScience Center, their engineers, and Marcus and the experts, I think we can really bring the world one step further. And yeah, thanks for your attention. And yeah, it is fantastic that we can give the world a real third representation of spatial-temporal things. And that representation was already there for many decades, but not used for everything, not used for computing, doing simulations. And I'm sure we can do this and that we can give the medical people better analysis tool for making diagnoses, or astronomy people helping to discover what happens there. Okay, this was the overview. Sorry if I took more time than planned, but somehow it's important that the techniques that are, say, the foundation of the proposal are clear, and maybe we can imagine better techniques. So there are alternatives. Not sure if there are any reactions at the moment. Online, offline. In the meantime, I will look for the next presentation. Oh, that's Marcus actually. Yeah. So make sure that Marcus can. Yeah, it's possible. So if there are no questions, let's switch to the next presentation. That is by Marcus Schutz from TU Vienna on research in the visualization of point clouds, large point clouds. Marcus, you should be able to share your screen.
Mm-hmm. Okay. Can you see the probably the wrong screen, right?
Probably I should stop sharing my screen. Yeah.
Okay,
yeah.
Can you see my screen now?
Yeah.
Okay. Yeah, hello everyone. I'm just going to talk a bit about the point cloud rendering stuff that we've been recently doing at TU Wien. In particular, about continuous level of detail rendering, progressive rendering, then computer-based rasterization, and some future work. So Peter already showed a little bit about this continuous level of detail. What we've been doing with continuous level of detail is trying to render semi-large data sets, in this case just about 100 to 200 million points, in real time and without those discrete level of detail artifacts that you get, for example, in Poetry or also other level of detail viewers, where you have blocks of points popping in and popping out. And the approach we took here is actually the data structure is still a discrete level of detail data structure. So to the left here, you can see we have 4 different levels of detail. They're discrete. And the way we get continuous level of detail between these discrete levels is first, we just discard points at a certain distance if their level of detail is too high. So in this case here, you can see we have a very high level of detail, and at some distance, we're just capping all the points. Then the next highest is capped, and so on. But this still gives us discrete levels of details and these harsh transitions from one level of detail to the other. So what we're doing is we're just using some heuristic to discard points. And the closer the points are to the border of the level of detail, the higher the chance that they are discarded. So by just discarding the points according to that, we can now get this smooth transition from one level of detail to the next. And we're also doing this based on the distance to the camera and also based on the distance to the center of the screen. So when we're doing this with both here, we end up with something like at the bottom right image here. And this is particularly nice for virtual reality, because in virtual reality, we need fewer details at the periphery, because for one reason, we can't perceive that much detail in the periphery from the eye. And the other reason is that due to distortion by the lenses in the headset, we also get a lower resolution in the periphery anyway. So in this video here, you can first see what it looks like with discrete levels of detail. And the next thing you can see about the same number of points rendered, but with continuous level of detail. And now when you move around the scene, you can hardly see that points just appear in a point-wise fashion compared to the node-wise fashion that happens with the discrete levels of detail. So yeah, I'm just going to jump to the next approach now. So this was continuous level of detail. What you also wanted to do is we had some semi-large data sets, so let's say up to 1 billion points. And generating level of detail structures always takes a bit of time, so minutes to hours. But we want to be able to take a look at things right away without having to wait for hours. The problem with 1 billion point is you can't really render it in real time. So with progressive rendering, what we're trying to do is we're not rendering all points in every frame. We're just rendering a random subset in each frame. And with reprojection, we're going to take the previous frame and then reproject the data that we've already rendered into the current frame, because the points from the previous frame, they're very likely to be visible again. If we move around in the scene, we will end up with holes after reprojection, because some parts of this model that were not visible previously. And now we're just going to render some random points in order to fill these holes here. So instead of rendering all 1 billion points in each frame, we just need to render different random subsamples of 10 million points in each frame. And this is how we can guarantee real-time performance. And at the same time, because of the reprojection, this will eventually converge to the full result, as you can see to the right here. And the nice thing here about this is also that with level of detail methods, typically you don't converge to the full result. So you'll always get to see some subsample data. But with this progressive method here, it will always progress to the full result. And here's a video showing that, where we load 400 million points. And we can already watch the data in real time while the points are still being loaded. There's no level of detail structure here. It's just sequentially stored and loaded. And because of the progressive rendering, we can render that in real time at all times. So right now, we've been rendering about 10 million points per frame to fill the gaps that appear after moving around. And if we reduce this, if you only render 100,000 points per frame, then you can see how it progresses frame by frame to the full result. But if you ramp it up to 10 million points again, the progression is so quick that you will perceive artifacts, but typically it's perfectly fine, especially in point cloud use cases. So probably not for games, but for point cloud rendering, that's perfectly fine. So the first thing I want to talk about here is compute shader rasterization. This is our most recent work, and we found that so typically when you render point cloud in OpenGL, you'd use the native GL points primitive as the fastest native way to render the points. But we found out that with compute shaders, you can actually render much, much faster than that. So here, this point cloud here, for example, is 140 million points. And with GL points, we only get about 9 frames per second. And with a compute shader approach, we get about 280 frames per second. So no level of detail, just brute force rendering of all the points. And we're about 30 times faster here with the compute shader approach. This also strongly depends on the order of the points. So the original order in this case here was pretty much Morton order. And Morton order is really bad for GL points because you have a very high locality. You have thousands of points to tens of thousands of points projected to a single pixel. And if you have 10,000 compute threads on your GPU trying to write to the same pixels, that's not going to work out well for GL points. But with the compute shader approach, we have some additional things that make this better. We also developed a shuffled Morton order here, which is just Morton order, but you group the points into patches of 128 points, and then you shuffle the batches. So you have good locality within a patch, but because you shuffle the batches, you don't have too much locality that would cause contention. And with this shuffled Morton order, the compute shader approach is not really faster, but the GL points approach suddenly gets about 10 times faster. I don't know, 10 times, 5 times here. So anyway, the compute shader approach works like this here. What we do is we encode the depth and the color value into a single 64-bit integer, and then we use atomic min to compute the closest point for each pixel. And what we end up with is a frame buffer that contains the depth value and the color value in a leaf fashion. So we just extract the color values, put this into the texture, and then display that texture. This basic atomic min approach here is still far from a good approach. You can still do some stuff like early depth testing before we do this atomic min. We can check the frame buffer. Is there already a point that is closer? If there is, we don't need to do atomic min because a single atomic instruction is slower than just a non-atomic read of the frame buffer, checking it, and then discarding atomic altogether or doing it. There's also a more advanced approach where we use subgroup communication. On NVIDIA GPUs, subgroups are 32 cooperating threads. So there's 32 threads that can communicate very efficiently with each other. So when we have 32 threads trying to render 32 points, what we do is we let the threads check how many pixels they are actually writing to. So if 32 threads are writing to one single pixel, then we're only doing one single atomic min instead of 32. If they're trying to write to 13, we're only doing 13 atomic min. And with this approach here, we were able to render this data set here with almost 800 million points or 12.7 gigabytes at robust frame rates of about 60 frames per second, so just over 60 frames per second. And the nice thing here was that it was completely viewpoint independent. So you could move around wherever in the scene, and it was always about 62 frames per second. With other approaches, so with the basic atomic approach or also with GL points, the performance highly depended on your viewpoint. So if no points were in the view frustum, you had a relatively good performance. But if you zoomed out, the performance would get worse and worse, not just because you had a lot of points on the screen, because you also ended up with a lot of points being projected to a single pixel. And this is what's really making things slow. So now some future work. So something that I've wanted to work on for a while and which I've recently got started with is simultaneous LMD generation and rendering. So For super large point clouds, 100 billion points or maybe 1 trillion, we still need to generate level of detail structures. But what I want to do now is to generate a structure and also at the same time display the results right away, and then focus the level of detail generation on wherever you're currently looking at. So zooming in somewhere, then generate a level of detail from this region right now. And another thing is I'm also currently working on Poetry 2, which is a rewrite because there's WebGPU is going to be released next year, and it's going to be replaced to replace WebGL. And there are very nice things in there that I want to take advantage of. Also considering switching to the new COPC format from the Howard Butler and his company, which is essentially a streamable level of detail stored in a single LIC file. So it's still a standard LIC file. It can be opened in any application that can open this file. But at the same time, you can just stream out the points that you really want as an octree, just like the Poetry format. And that's it. Thank you for the attention.
Any questions? The visualization, the music elements? Not in the room. I don't see anybody. Yeah, Fedor?
Marcus, you also do in Poetry, you also have some analysis options. Are you also taking those into consideration, or are you mainly looking at view?
Can you repeat the question, Peter? I can understand it.
Yeah, sorry. Yeah, the question was currently in Poetry there are also analysis functions, not only viewing functions. And then also these analysis functions we included in your new version.
Yes. So I want to keep all or most of the measurement tools and analysis tools. It can be that the very first version of it might not include all of them, but eventually I want to re-implement all of them and maybe some more.
Okay. Other questions? No? Okay, then Marcus, thanks again for your presentation, and look forward to the cooperation in the project. Could you unshare your screen?
Yes, already did, I think.
Okay, then we move on to the next presentation, which is by probably I should share my screen now here again. Share screen. Yeah. Okay, we did a lot of work, and basically when we say we, it was often Hai Cheng the last couple of years. So Hai Cheng will now explain what he did during his last 4 years in the PhD research on managing point cloud data sets. Cheng, the floor is yours.
Okay, hello everyone. It's my honor to be here to present briefly my results. So today I will present from three aspects. So the first is the histogram technique to solve the querying on non-uniformly distributed data. The second one is besides the window queries, we also explored the polytope queries, which incorporate arbitrary query geometries. In the end, I will present the benchmarks and how we use the other solutions to solve real-world problems. So, Peter has mentioned the method for nD-PointCloud management. Here we call it plain SFC. So as you can just briefly repeat. So using the space filling curve, we can encode the coordinates of a point from 2D or 3D or even ND into a one-dimensional K. And then we adopted the IoT structure to organize and manage all the data using this K. So this is how we manage the data. And then when doing queries, So the plan SFC adopts the mechanical way to decompose the space to generate the ranges. So it just recursively and mechanically partition the space to approach the pure geometry to derive the 1D ranges. So you can say the problem. You can see the problem. Plan SFC doesn't know where the point is, so it can generate a lot of ranges without any points inside. So this ranges contributes nothing to the result, but takes quite a lot of time in range computation, which slows down the whole curing performance. So what we think is actually to build a ND histogram structure. Here we call it a histogram tree to record the point distribution information using a tree structure. And then when computing the ranges, we use this tree structure to smartly generate ranges considering the points distribution. As a result, we get all effective ranges with very few range containing no points. So this is supposed to improve the curing performance. So going back to the whole workflow, so we basically modified here. During the range computation, we use the histogram tree to generate the ranges. And then we want to know, right? Not every point cloud needs this histogram tree technique because, for example, if point cloud is uniformly distributed, why should it know where the point is, right? So we want to know when is the most effective moment for using a histogram tree. Then we propose a uniformity metric to describe the point distribution, how uniformity the data set is. So it's basically based on this equation. Here the Fn is the joint probability density function. And then we also establish the effectiveness of a histogram tree based on this formula. So as you can see, if there are a lot of non-vacant ranges, then we don't have to use the histogram tree basically. But later we establish the theorems and show it shows that when points are skewnly distributed, so where the CHC is very low, then we do need the histogram tree. We establish the theorems, and then we perform the simulations to verify our theorems. So we simulated the different dimensions using those distributions. So these are the extreme distributions, also uniform distributions. So we construct a data set using these distributions. And you can see from this table that the data set constructed has a different CHC value, which is the uniformity measure we established. And the smaller the value is, it means that the data set is more non-uniformly distributed. And as you can see, according the result, that the data set with a very small CHC value needs the ND histogram the most. That's our simulations. And then, as I mentioned, besides the window queries, we want to explore more possibilities for curing. Another important query geometry is the polytope, convex polytope. So what is it? So a convex polytope is consisted of a set of half spaces, and each half space is expressed using an equation like this. You have a vector and then a scalar to express such a half space, and then a polytope is formed by several the overlap of several half spaces. So to solve such a query geometry, our idea is straightforward. So we generated the ranges by approaching the geometry by subdividing the space recursively. But then the problem is that how we can detect whether an ND cell intersect with the boundary of the polytope. Then we establish the algorithms for such intersection computation. The first one is we call it sweep. So basically, for example, a histogram tree node, we detected two points. One called entry and the other is exit. We use these 2 points to compute the distance from them to the half space to detect whether the node intersect with the half space. So in this way, we can save a lot of computation when the dimensionality is high. And but it has a problem. As you can see here, the N4 cell satisfies all the half spaces independently, but in the end, it doesn't actually intersect the polytope, and it could only be filtered out in the secondary filter. The next algorithm is more straightforward, called sphere. We just generate a hypersphere for a single node and detect whether the sphere intersects the half space. And then in the last we also tested the Cplex, which is a software from IBM. We basically established all the boundaries of the half spaces and also the cells into a set of constraints. And then we use Cplex to solve the problem using the linear programming method. This is more rigorous than the sphere and sweep. Here's a simple result comparison. So A shows the Curie geometry, and B is the accurate results. Well, the orange ones are selected by Cplex with a bit more false positive points from sweep, and the most from sphere. So sphere is the most coarse method. Starting from here, I will show some benchmark results. This project is mainly based on and will based on AHN2. So I also tested it here. So the data set contains 10 billion points, and as introduced by Peter, also Marcus, I also added a CLOD dimension to each point using the distribution, the half distribution. And then we established different Curie windows. That's the window Curie with a different selectivity on different dimensions to explore the performance of our management solution. So I will explain a bit here. So the first solution is PostGIS. So basically, we adopt the 4D multi-point object to group a set of points together. It's 4D. So in this way, we create a 4D block approach. And then the second and third a solution is pyramid extension. So basically, proposed from computer science domain. So they proved that these methods are more appropriate for data in very high dimensional space. And then here's the plan as and then the plan FC, and HISTA-FC means plan FC with our ND histogram. So as you can see from this the results that plan FC and HISTA-FC in most cases perform the best, but still the conventional ones like PostGIS can be fastest in certain cases, because the main drawback of PostGIS lies in the block approach. It spends a lot of time in unpacking these blocks, and that's the important finding, I think, of during this benchmarking. Those block-based approaches need to unblock, and it can really take a lot of time. Then the perspective view selection. So basically, we want to see more points nearby, well, less points, but more important points showing far away. So we realized this using the polytope technique, right? It's a 4D geometry. And we tested a close up where you stand in the street and looking forward. Well, also a bird eye view looking down from the sky. So these are some visuals, and we realized that what we want, that nearby points will be all rendered, or far away less points. But here it doesn't cause too much, deviation from truth. We think the point cloud can be more generic instead of the conventional ladder data. I think the modeling data set can also be represented using point cloud. For example, the flood modeling results, where we use to analyze the flood risks. So we need a really huge modeling database to support this. But the conventional, but as this contribution normally based on mesh, right? Those triangular cells, they are more accurate for flow computation. So if you use rasters to store this data, then you lose accuracy and you spend more space on the empty cells. So I think so we propose to extract the syndroids of this each cell to form a nD-PointCloud, right? That's the thinking. So it includes 8 dimensions. Case ID means the conditions to simulate. You normally imitate a certain condition and then you run the model. And also flow velocity, depth, and their direction totally around 0.3 billion points. So we test the different cures as well. They are important for risk analysis. For example, we want to know where the flood depth larger than 3 meters in a certain case. And then other important queries, especially the last one. So we want to select the dangerous locations which are evaluated by the product of depth and velocity, because only depth, for example, if the depth is 3 meters but no velocity, so a human can swim. So it's not that dangerous. So they use product to evaluate how dangerous it is. So as you can see here, we adopt the HistoFC, PlanFC, so with the nD histogram, no nD histogram, and Oracle's SDO-PC based on the 2D XY organization. And this time, due to the skewed distribution of water depth, water flow, and more dimensions, as I mentioned, you can see that the HistoFC overperformed the PlanFC more significantly. So you need to use such a technique. And then other results. So for certain results, still, depending on your selection, the conventional block-based approach can be still competitive. The last one is based on the product of depth and velocity. We also use the polytope modeling. And finally, we achieved also very efficient response. Okay. Yeah, thanks.
Are there any questions?
I didn't quite understand how you got to the velocity.
Flow velocity.
Yeah.
So basically, every cell you will get one velocity value. That's computed by a hydrodynamic model. No. It's based on a conventional modeling, but because they, yeah. That's. But then I don't know traditionally how you like hydrologists like you to manage that data. I don't know your solution.
Yeah, we have several approaches to deal with
Uh-huh.
topography. What you say, grid-based or 1D based or catchment-based. Depends a bit on taking into account the detailed resolution of the terrain is one of the open challenges.
Are there more questions, either in the room or online? I think it is the case. So thanks again for showing this overview of your research. And now we move to the presentation of Vitali. Vitali is Mercado. He will introduce himself because he is the most important person in the project. So the only one that works 3 years full time on the project. So Vitali, the floor is yours.
Thank you so much. Well, thank you so much. It's a very honor to be here. I will introduce myself a little bit. This is the outline of my presentation. I will talk about me, and then about my PhD, and then my vision of this project, how I think I can contribute in this project. So this is me. I'm Vitali Diaz Mercado. I'm from Mexico. I did my bachelor's in civil engineering. So then I moved to water sciences. I did a master in water sciences because I was very interested in water and topics related with water. As you can see, I switched between structural to water, but it's STEAM civil engineering. And then I realized that water likes too much to me. So I started to do a specialization in water management. And then I was looking for something to do a PhD, but something related with water and computers. So I found hydroinformatics in IHE here in Netherlands. So I started my PhD in hydroinformatics. So as you can see here, some keywords in the titles of my thesis are data, modeling, and basically maybe not very easy to see, but also spatio-temporal variations of the phenomenon. Well, I will talk about a little bit about my PhD. I did my research in spatio-temporal characterization of drought. So one thing that we have to know is that drought is a regional phenomenon. What that means that a drought has a spatial extent, and that spatial extent changes over time. So drought occurs basically everywhere, and with several consequences for human or for also environmental aspects. So basically, nowadays, drought monitors are able to provide information in order to have to develop mitigation plans. So drought monitors provide information about the intensity, duration, and also the spatial extent. Drought monitors basically generate information, and that information is stored, and we can use that information in order to characterize drought, in order to develop new methodologies for spatio-temporal characterization. And also another related data, for instance, results from regional or global hydrological models. We can also use that information to characterize drought. And also there are more information, for instance, those generated by remote sensing or for reanalysis. But there is still some gaps. There are some gaps that we need to fill. Those gaps basically that we realized that we need methods to characterize drought explicitly based on the spatio-temporal features of drought, as the spatial extent of the pathways. And also we need methods to monitor and to predict drought that consider that those spatio-temporal features. So basically, we propose a methodology in order to build the spatial tracks. This methodology, basically, for this methodology, we use the rasters grid data, And we calculate the cells in drought. So all those cells that are in drought, we identify those cells, and then by using a clustering technique, we identify the clusters that we call it droughts or 3D droughts. And then we identify the largest ones. And then we propose the centroid of those areas as the location of the drought. And then we propose the methodology to link those centroids in order to build the tracks. So that allows us to build the spatial trajectory of every drought. So this is one slide of some results. We applied the methodology in India. What you are seeing in the top is the evolution of the drought areas in red, and the centroid are in blue. So we test our methodology with data related with historical droughts in India. And this is our three combination of the parameters. And we calibrate with a number of droughts, and we validate the methodology. So this methodology allows us to characterize, to build the trajectories of the largest drought events in India. These are another results. This is for South America. So what you are seeing here is the cluster of one of the largest droughts that occurs in 1957. So in the set, you are seeing the time. So you can see the evolution of the droughts. And this drought is, you can see, is full of porous. So the drought is changed over the time. But you can see here, as I start this presentation, mention that drought is regional. So you can see also in the lines, the trajectories of the centroids of the drought areas. That changes all the time. As you can imagine, we now are calculating more features of the drought. So we have not just duration or onset, end, or the intensity. We also have, for instance, the spatial extent. We also have the number of clusters. We also have, we actually propose a methodology to calculate the distance between clusters, and we use those distances as a way to measure the porosity or the density of the clusters. So we are not able to analyze visually the results. So we propose some visual tools in order to help those are interested in drought to analyze the variation of the drought. So we propose these three diagrams that help us to identify, to analyze some spatial patterns. For instance, we can analyze periodicity, zonality, persistency. But also, those graphs help us to identify some hotspots, cohesion, fragmentation of the clusters. But also can help us if we, for instance, apply this one of them in two regions. We can identify similarity or dispersion or trend. So basically, these graphs help us to analyze visually the variation of drought. So I have to say that in order to build those methodologies, for instance, the tracking, we are using some machine learning techniques. And this proposed scope opens a new area of potential for drought prediction, because now we also are interested to predict not just the duration, not just the intensity of the future drought, but also we are interested, for instance, we can build the methodology, and we are proposing some approach to build a methodology in order to predict, for instance, the future location and the future spatial extent of drought. And this can be used for monitoring. And now the connection with this nD-PointCloud data. So basically, maybe I didn't mention, but to build the methodology for tracking droughts and also for the characterization of droughts, I use rasters. But we have to transform or to make some transformation on the rasters in order to extract centroids and other features. And basically, we use those features to characterize drought. So the connection is that at the end, we are using points and also features in order to characterize, in this case, drought. So I found this connection. And also because we develop methodologies to characterize or to analyze the spatio-temporal variation of the phenomena, in this case, drought. So we are now interested to move to also, because one of the applications of this project is not just visualization, because we can take advantage of that, but also the analysis of the variation. And I found this, for instance, these examples, this department, we can use this previous information in order to provide, in order to build, in order to analyze, for instance, the spatio-temporal changes. In this case, for instance, is spatio-temporal changes of every point, but we can also analyze spatio-temporal changes of water levels, for instance, in the coastlines. We can also not just to use directly points, but also we can use the points in order to calculate some features. For instance, this is one paper where they use points in order to calculate the diameter, for instance, of the trees. And those features that are calculated based on points that can be used in order to monitor, for instance, the environment. And also we can use the queries that Heinche developed for or to do this kind of queries for flood risk management, which are very important in this case. And also we can use the point cloud for hydrological applications. So as you can see, also this is one of the theses, MSc thesis here, that developed here in this department. You can use points to calculate the streams, but also to delimitate watersheds. So basically, we can use points, not just to manage the data, but also to propose some methodologies to analyze the data for water-related phenomena. So, yeah, thank you very much for your attention.
Any questions? Online? Yeah.
Now you calculate the set with the drought. If you have two droughts moving at the same time, how do you do that?
With the tree, I didn't mention maybe, but for instance, these results is by using just one, the largest one, and the result is using the 3D. So we solve it like this. So we can calculate 3D, and then we can monitor each of them. And this is just the largest one, because as in many other phenomena, we are interested in the largest or in the extremes, basically. No, in all the, no, all of them. We are interested basically in the extremes.
I also like this diagram on the left side. This one here, space-time together, where you can see whenever was there a drought. Of course, it's hard to imagine the projection of the bottom helps. What is the location between the slicing tools and
change.
More like space-time.
Space-time together, that's good.
It's not so technical question, but I was wondering when is a drought finished and is the next one start?
Yeah, this is a very interesting question. Yeah, because now the results, not by me, but on other colleagues, they are making research in order to use those previous results in order to know if the droughts repeat the patterns, because then if we see some development that is very similar to one previous that occurred in the previous part, maybe we can say, okay, the next step or the next trajectory or the next location will be this.
The question was, is there an end? So repeat this like I'm continuing. Could it be a time, so if there's no drought, and I think that is if there's sufficient rain. Okay, what is the definition?
Yeah.
Like if you have hurricanes, there's hurricanes all the time, but there's specific hurricanes which move from A to B, and then there's a next one. And I can imagine for drought it's the same. It's not the same drought for 10 years.
Yeah, actually, there is one kind of season of droughts when the droughts occur. We can discuss more about it, but in this previous study, we found that droughts occur more or less in 1 month, and then more or less in other month, more or less, like the hurricane, as you said. Yeah.
Okay. Other questions? If not, good luck with your project, with our project. And also good luck with your PhD defense next week.
Next week.
So you're an early postdoc already, but it all will come good, I would say. Okay, now it's time for Niels Dorst from the East Science Center to say a few words from the East Science Center about the organization of the East Science projects, how to collaborate. Niels, not sure if you want to show some slides or just give a...
Yeah. First question is, can you hear me, of course?
Yeah, very clear. Yeah.
Good. Yeah, let me just share some slides. Share.
Yeah, looks good.
Good. Yeah, I guess you have the bar. Right, I'll just make this quick since we don't have a lot of time, I think. Just to give some background on what the East Science Center is and what sort of projects we do, to also just get a bit of an idea on why this was one of the projects chosen. So the East Science Center is funded by NWO and SURF. So basically this makes us a merger of science and ICT. So NWO is the science funder of the Netherlands, and the SURF is one of the ICT providers for research. And I think this is also very much in our DNA as an organization. We really try to bridge scientific research and ICT. So really trying to combine these things and try to generate basically more research and better research and more breakthroughs by the use of this advanced ICT technology. Primarily we're for Dutch universities and a national center. So anybody in the Netherlands can work with us. But what we really try to do is really try to better all of research internationally and nationally. So it's not that if it's not for a Dutch person, we don't do it, but or somebody in the Netherlands at least. But mostly of our funding actually goes to Dutch scientists. And just to give an idea of the scale, the East Science Center is about 90 people, probably 95 by now. So this also is reflected very much in our vision and mission. I won't repeat it here literally, but basically what we're trying to do is create a robust community where basically everybody's able to do this sort of research themselves, which I think also why this PointCloud project is a really nice project, a really good example of how by making this sort of infrastructure available, more people can do more things, more research, but also companies like Deltaris. And what's important on this slide is that we kind of have two sides of the coin that we do work in. So there's this ambition 1 and 2. So one is basically what this project comes from, a call. So we do these big calls for projects, and people can basically put in a proposal. What is good to say is that we have two different kinds. One is one very driven by the domain call, so a research question that people are trying to answer, and then we try to help them with coming up with the answer using whatever technology is needed. That's not one of these calls. So this project actually comes from a call where it's kind of the other way around. So we have a technology-based call where basically we say, well, we would really like people to help and promote and build a technology that then can be used further in different projects, either by us or different people altogether. basically trying to build the tools and the technology and the infrastructure needed to do research. We do some other calls as well, like very small calls on this machine learning or optimizing software. So for more information, you can always go to our website. And the other part, which also could be interesting for this project, is we do a lot of workshops and training. So since we're only able to help create a very small part of research and a very small part of scientists, we also really try to do workshops and training to try to build capacity at the different research institutes on how to do this. We also have a lot of knowledge and expertise on how to build tutorials and how to do workshops well. So this could be something interesting for this project as well. And since we're actually a pretty small organization, we actually also do a lot of local capacity building. So we train the trainers in being able to give these trainings to eventually the students, PhD students, staff, and that sort of thing. And these are the sort of things we teach, from very basic skills to more advanced level things. And results of project could also be one of the things that we could build some kind of program around. And then the role of the eScience engineers, somewhere in the agenda, I think there's an item on who will do what in this project. So for that, it's good to know that our eScience research software engineers are really people that are kind of also, just like our organization, sit in the middle between ICT and research. Almost all of them have a PhD and a lot of knowledge about the different ICT developments and about building software. They're very collaborative, so we really try to partner with organizations and really together work on this research project, rather than the alternative where basically you give us the design and we implement it as an application, right? So they're definitely not code monkeys. And one important thing about the Science Center is that we're very much for fair and open science. And this also you see in the engineers, they're really passionate about sharing things, about making things open, making them available, that sort of thing. Now some of our expertise that we could make use of in this project. Machine learning is of course very often used recently in research, so we have quite some knowledge on that, but also computing, HPC, using of GPUs and other accelerators, analytics, big data, text analysis, visualization, data processing, software quality, which is also important because it's great that you have a prototype, but if you want to get it in the hand of users, it's very important to actually get it to be of a sufficient quality so people can actually use it. And then, as I mentioned, the open science fair, how to make software sustainable, that sort of thing. We can also help with that. Then a recent thing is that the eScience Center has basically organized intersections where we work on the different domains. This is also why I'm here today. I'm the program manager for the environment and sustainability section. So I try to take care of all these projects in the section. But we do have a lot of other sections where for this project, if it turns out that it's beneficial to use this in some other projects, we can always get into contact. We're not split into sections, we're more sorted, I would say. Then something about a project life cycle. So today is the kickoff meeting. Very nice that we finally having this kickoff. Unfortunately, it's kind of hybrid, half online, half offline, but still. At some point in the near future, we should start thinking about having some kind of software management plan and data management plan. You may know from the European Union projects as well, especially data management plans. And these are not per se a very formal thing, but what we try to do is kind of think about, okay, what software are we going to build and to what quality, and how are we making sure that during this project we build all this software in such a way that's actually usable by others, and the same holds for data. So it's good to kind of think about explicitly. And there's a project review every year where we really try to see what are the results of this project up till now and how can we help make this even better. And then there's a final report in the end, which is basically mostly to make sure all the financial aspects are done correctly. Right. So now maybe Thijs, you want to introduce the team of engineers that are going to work on this project?
Yes. Shall I share my own presentation of this, or do you want to?
I can just press the next if you say.
All right. So you'll notice, and so I don't want to kind of take away the honor of Mert and Francesco, because those are, it's a really nice example of the collaborating that happens within the eScience Center of engineers that want to join in of their own interest. They join because of their interest in PointCloud. But this team CAT, is the team that I'm part of, and they have a lot of background in visualization, which is probably something that will be beneficial for this project, and where the eScience Center can support the research effort. So these are the 5 people that are part of the team in alphabetical order, maybe so I'm last. Introduce myself last. And I've added some cats because I don't have any specific, or we don't have a specific cat team logo, but obviously the internet's full of cats. So share some of them. And then for projects, I won't really go into earlier projects that we did, but via API Revisited is a project that is recently coming into completion. And this is a very nice project of point clouds, specifically where we did some nice 3D visualizations of point clouds. But that's probably something for another presentation to go into. But if you want to press next, then I'll go over the different people. So first off is Jesus. He's our specialist in UX research, so user interaction. And he has a lot of experience in web applications as well, visual design. And for the next one is Maarten. Some people might know Maarten from poetry development. I think he worked together on poetry. I'm not 100% sure. So he has a lot of experience with point cloud visualization. And then for the next, I'll go really quickly because it's already a long day. Peter, he's very good at data visualization. So he should be very useful in this project to correctly show what we actually want to show of the data, because there's probably not just a lot of data, but also different aspects of the data that might be important. And then next is Pushpanjali, and the fact that she has fewer items doesn't really do her justice, because she is a really good web developer, but her expertise is more often useful for other projects. But she's great for the web development and visualization aspect. And then finally, for my key skills, so I already said a little bit during my introduction that I come from a computational geometry background. During my PhD, I built a 3D or a viewer for showing the results of my surface reconstruction work. And then I've continued similar work later on. So yeah, that's the whole team.
Thanks. Right, so that's all I had. Also, just to make sure we can continue this presentation, this meeting. If there's any questions, I'm happy to hear them. But do repeat them at the desk where I can hear them. Yeah. Very hard to hear the audience.
Far away voices. Yeah, it's a good suggestion. It has been a long session now, and maybe people really need a coffee or tea or go to the toilet. So this is kind of the structured part, and after the break we just have say open discussion on, for example, yeah, what application domain do we, or specific topic do we have in mind first, or What is the topic of the first sprint we want to organize probably early January? What data sets are we planning to use? So really many open topics. What software are we going to use? Database, are we going to use files? Which database, what viewers, things like that. So let's have a break. Let's see if we can get a coffee or a tea nearby. And it is now 10 minutes to 4 or 8 minutes to 4. Let's come back together at exactly 4 o'clock for probably half an hour, maybe even less. Yeah? Okay, see you in a few minutes, 8 minutes. If they do or not, do not bring coffee or Yeah. Okay, welcome back after the very short. I stopped wearing my mask. So welcome back, everybody. It was good to have a short break after all the presentations we had, all the introductions. I'm also happy to see our head of the department, Michiel Kreutzer. And yeah, he could not be at the beginning, but it's very nice that he is now present. And maybe nice, Michiel, if you can say some words of welcome to the team members. And Michiel is our head of department. You're muted, Michiel.
Yeah, and I just started in this role, but I've been able to read through the proposal quickly. So this is a nice collaboration between the eScience Center with very interesting, very computational objectives with respect to point clouds. I think also Deltares is involved, so it's a nice collaboration of many partners pursuing a research line that, of course, Peter is an expert on and has been an expert on. I'm sorry I was not able to attend all of the meeting, but I'm really happy that you could start. And at least I see some people present. So
a few people here still.
yeah, I mean and it would have been much nicer, of course, if there would have been drinks. But I think I hope at least you have been able to see faces and to somehow meet and get to know each other. The project runs for 3 years, Peter.
Correct. Yep.
Yeah. So so I wish you lots of success and fun. Seems to be an interesting topic. How to see if you can, collect the data and keep it as point clouds, and then I think that's the gist of the project, right? That you then want to on the fly be able to
not convert it to other formats, but use it directly. Yeah, and, yeah, we want to test that in many applications, but to start with water management related challenges, as there are many point clouds collected for that purpose.
And the computing infrastructure to do that, will that be in Delft, or is that with Amsterdam, or how's that organized?
I think it's a very good point. What hardware will we use? And we have our own server, which is a bit older now, but okay, Delft is building the supercomputer. And as architecture, we have about, use rights, 6% of the total, but it's a big computer, so 6% is still a significant amount computing time. And we should in contact with them, but we also in consultation with the experts from the eScience Center, the high performance computing experts, what they recommend, because that is not my area of expertise.
Okay.
We have a lot of data, and let's say change detection or flow computation can take really a lot of time, and seeing how we can do things in parallel or use GPUs for doing these kinds of computations are unique opportunities. But that's what we want to figure out in this project. So indeed, a very good point. And what may also be interesting is hopefully that the eScience research engineers are also, say, depending on the coronavirus rules, 2 or 3 days per week here in Delft, so that they are really our colleagues.
Okay. Yeah.
And that is also what I like about the eScience Center, and that these research engineers go from one university to another, and maybe what they have learned before in the medical application, is what they, or in astronomy, that knowledge they bring also to us and put it in our project. And what they now do in this project can also be reused in other domains in the future. So it's really a very nice setup.
Okay. That sounds very good. So and of course, well, we can host them, of course, but that's taken care of. I hope.
I think we have nice spaces for them, and as soon as we are clear with the coronavirus rules, because it's important that we can talk to each other, especially in the beginning, and person to person, face to face.
Yeah.
Also with Deltares to figure out, okay, what is our exact use case, what data sets, what functionality would we like to realize.
So in that sense, I'm really happy that this meeting could go through still immediately after the press conference.
Difficult times.
It could be worse, but of course we Delft gives priority to research and teaching, and if we can keep the place running in that sense, that's for us the most important. So we're going to focus on keeping research and teaching going the coming weeks, and so if that requires some coming together, I think that we can facilitate that in a safe way if that's possible. But parties are off, so then you have to go. There's plenty of avenues for that close to Delft or Amsterdam.
Yeah, clear. Okay, thanks for the support, Michiel. Thanks a lot.
Yeah, I briefly read the proposal. It looks great. It sounds like a lot of fun, and I hope I can join when you get some results coming in. I'd love to be updated on where this is going.
Yeah,
and I think it's a really nice collaboration, Peter. So thanks for reaching out with the other partners, and lots of fun and lots of success.
Thanks. Look forward to it. Much appreciated. Okay, open discussion. So one good point raised by Michiel already is okay. We have this vision of the open point cloud map that needs infrastructure. So what would be good tools to start working with? I'm not sure at Deltares if you have facilities, or at the eScience Center if there are facilities. We have our own facilities, and maybe that's even good that we could mimic a distributed setup. So a node here, a node there, even maybe different operating systems or different data management platforms. But if we talk the same communication protocol between servers or the multiple servers and the client, then that should not harm and even be nice to prove that it's such a heterogeneous setup. It can work. Maybe from the eScience Center, any reflection on the topic of this hardware aspect? What?
Shall I start?
Yeah,
so,
yes, please.
So I think the first thing to note is that the eScience Center has no hardware except our laptops. And this is also on purpose, since this keeps us both flexible, also kind of independent. So we really try to make the best use of whatever infrastructure is available. We do have a lot of connections with SURF, obviously, since we're also partly funded by them. So we do, we do have like a short kort lijntje. What's kort lijntje in English? I don't know. We have we have good connections with SURF, so we can just figure out what's the best infrastructure to use here, and we can just request it using this e-infra thing. But so then I think it's also good to make an inventory of the type of infrastructure we need. Do we need like the server type 365 days a year, or is this more the incidental computing, which may need a very different infrastructure?
Yeah, exactly. Different challenges need different solutions. Somehow, if we want to host continuously all the data and serve it to all the users, and we need something permanent, but maybe not super fast in computing. So if you can use other nodes for doing the analysis or the pre-processing, if we need pre-processing, and serve that then from a rather, say, modest machine, maybe even the one we now have already for the AN2 data. which I'm still happy that the TU Delft is also financing that, because we have this machine still up and running. I think that is 5 or 6 years after the previous project. And especially in the beginning, it was used quite well, the AN data, because there was no real other online AN viewer, which was capable of doing 3D, and also the additional functionality that was added to the viewer. But okay, after the project, gradually it became outdated, a new version of Poetry, new version of AHN, and probably in one of the first sprints, and that's maybe the second topic, and we can see, okay, can we at least upgrade the current or the previous project results, or the current system, into, say, a more up-to-date version, new release of the software, new data sets. And probably first on my agenda would also be some nationwide change detections. It's kind of fun to see what has changed in the land. And to see it everywhere. It is, so maybe that is sprint 1 and 2, I don't know. And yeah, what we should also put in the agenda, maybe already in December, I think TU Delft and Deltares, and maybe also Science Center, but for sure TU Delft and Deltares should think about, okay, what use case is most promising to be addressed with point clouds. We tried flow computation, stream elimination, change detection. Yeah, maybe it's a bit, yeah, this is the open discussion thing, yeah? So maybe, yeah, Fedor, do you have any clues? Maybe if you stand up then, because otherwise I'm sure they will not. No, it's here, it's in this thing.
So there's, let me just stand up here. So there's several challenges that are, that we face with. We have the global dam that Maarten is working on. And so that's important for the global flood models that we're working on, so that you have global coverage of all the hydrodynamics. So that's a really interesting problem. And that is probably done with the ISOT point cloud, so these profile measurements. It's also relevant for our global reservoir data sets that we're working on to scan over 1 million reservoirs around the world, to see how much water is there available all around the world. But also on a local scale, for example, now we know that several water boards are still using HN2 for their flood simulations. It would be very helpful in the Netherlands to show them why they should redo their flood simulations, because there's this new building, there's this new terrain. And so that is also a use case that let's say is relatively easy to start with.
But if here I said on one hand and AHN on the other end, and how to make that fit together, and it's already quite a challenge in one environment. I think I said the laser beam footprint distance is 80 meters on the ground, depending on where you are and what direction you are looking. But and AHN it is very different. So it's maybe 20 centimeters or so spacing between the laser centers. But I said it's very interesting also, maybe because of the temporal aspect. So the satellite keeps on turning and turning and making loops around the world. So that is also generating nice temporal time series. Did you already check these versions, say same area scanned twice? Or
Let me stand over here for answer. So ISAT is a nice data set to use. Now it's 2 years of data, but if you want references with AHN, indeed there's a temporal aspect, but there are also geoids to actually correct for.
Yeah.
Because it's ellipsoid based. So that would be one interesting transformation already. Indeed, there's sparsity. So there is a point every meter, depending on which data set you use. The footprint is roughly 15 meters. While 15. For AHN, it should fit in my hand, basically.
Yeah. And say revisiting the same location.
Nice.
exactly.
Is it not happening, or?
They try to point the basically the laser away from the exact beam footprint they have on the ground. But the revisit time is like a month and a half or something, but they will never be exactly at the same point. They try to cover as much of the Earth as possible because in the
So
end,
they see there's additional points filling in the previous points.
Never exactly, no. But they will cross, but eventually they'll.
When they revisit, they see the same area.
The same area, yes, but it will never fill. It's a very sparse data set.
It's a different sampling of the same area.
Yeah.
So that would not be suitable to do change detection. Is that what you say?
Depending on what kind of area you want to change.
How big the change is, yeah.
Yeah, if you say a kilometer area,
you will see it.
Then that will work.
Yeah.
I've done that. That works. But if
changes.
Let's say a small parking lot like here, you won't have points to actually do that.
But lakes getting smaller and bigger. That is.
Yes, definitely. That's what we're doing with the reservoir monitoring.
Yeah.
So what is originally did.
Yeah. Okay, so that is, I think we had say topic 1 hardware, topic 2, okay, what specific application do we select? And we don't have to worry. First have to build the whole stack of solution, and in the end, we will try to build the application. But in the beginning, it's good to think, okay, what are the needs of the application domain, so we can make the right decisions there. Though we don't want to make a custom-made stack, so we want to make generic solutions. And when Vitaly was presenting the drought moving trajectory plot, I had to think of another type of point cloud that is moving objects, people moving around with their cell phones, mobile phones, or ships moving around, or birds flying around. That is also generating a huge point cloud, locations X, Y, Z, time, identity of the object, and also 4D, 5D at least. Not primary application area, but we think that our stack, our solution, will be able to serve these applications also. We mentioned a little bit the topic of the sprint. I think timing-wise, that could be, I would say, early January, when Vitaly is used to all our earlier developed solutions, the technology, the theory behind. Maybe it's even nice if allowed, and if, eScience people are. So in 3 weeks' time, there are new rules. Maybe the Prime Minister is saying, okay, you are allowed to visit if you show your QR pass again, and if eScience policy is allowing them people to visit or to work. So at TU Delft will be your workplace for some of the eScience research engineers, or the part-time workplace. So you're very welcome. And personally, I think it's also very important that we really work together, and not only in the sprints, but also during some normal day-to-day work. I remember very well the previous project, and we had Oscar Martinez Ruby from the eScience Center, and he was really sitting and in the same room, and we had discussions all the time during coffee and during paper writing, during coding, whatever we did, we had discussions, and I think that's good to have again.
Yeah, no, I agree, especially at the beginning, right? Once everybody knows what they're doing, and it turns into quite big chunks of work that you have to think about for a couple of weeks, then maybe you don't need as much interaction, but especially at the beginning.
Yeah.
And hopefully the rules relax slightly 3 weeks from now. Let's see. Smaller groups also easier, right, than big groups like this kickoff.
Yeah, and I think the 2R policy may be there then, and supported by the Dutch law, and then maybe, it's possible. Okay, let's be optimistic and do it as soon as possible. And if not, we do it online. That's for the moment our only option. Yeah, what other topics to discuss now? This is really the open discussion, so it's not only me putting discussion points on the table, but anybody can. So maybe the role of the experts. And so on purpose, I asked people from outside, from Oracle, from Esri, het Waterschapshuis, Geodon. Yeah, Marcus is kind of special from TU Vienna. He's kind of in the project. He was planned in the project for 2 visits to Delft. Yeah. And so what I have in mind with the experts, that we have, say, typically every 6 months, a say consortium or group meeting, however you want to call it, where we show the progress, we show what our plans are for the near future. And yeah, we listen then to the experts. Is this wise, this direction of development? Do you have suggestions for the developments? Maybe do you have data set? So if Cyclomedia said, okay, here we have this nice 35 or 40 trillion points with RGB. I said, yeah, okay, let's try. Maybe we have this. Maybe we have the supercomputer available. I will try to get access to that. And we upload the 40 trillion points in Delft Blue and start processing and connecting to viewers later on. And so the experts, they can contribute whatever they want to contribute. They're here because they are experts. And so I respect their opinion, but they may also contribute with software. So they have a software stack. What we could produce will be open. The code is reusable, but there is both good open source and also proprietary software with closed source solutions, which is there in the reality. Yeah, I also like comparing to learn what works and what does not work. So therefore, I like to be really open-minded here with the opportunities. I know also in the Netherlands, there is this from the government initiative to also, they're already sharing a lot of data, especially in the geographic domain, to even do that better in the future and also more in 3D. And also point clouds have a very important role there. And also het Waterschapshuis is involved in these developments as one of the, say, source data providers. And so maybe what we do in science and what is happening in the government community can be aligned. I would be proud if they would reuse the technology we develop in our resource community. First target is water management, but if other applications are there, very, very fine. And I also remember that Fugro was reusing our project results. Martin Kodde was using, say, PointCloud based solutions from the earlier project, and I think that's a nice result. Not per se only science, but also in industry for the benefit of the whole society. Also very open to collaborating again with Oracle. Very good memories also of the previous. And yeah, the world has evolved in 10 years, so maybe instead of having our own machines, we should think more of cloud solutions and see, okay, how can we then control these solutions when we're doing timings, how efficient our solution implements, how pure are the measurements, are we measuring other processes on the background? That's one of the things I have in mind, but maybe benchmarks or performance measurements are a lower priority than in the previous project. That's something we have to, so more functionality oriented and say, in general, good performance. Okay, that's a non-science terminology. So true scientist wants to measure and prove what is good and what is not so good. So, okay, these are my initial ideas. And yeah, as also said earlier, we have bought an iPad to do a little bit of our own laser scanning, as what also many future consumers will be doing, and not only consumers. I also can imagine that if architects, so my colleagues in this building here, see these tools and they see an environment, and they can make local scans, indoor, outdoor scans, and have really 3D models which they can then reuse in their design environment to change the world over there, that part of the world. It's also really unpredictable of the amount of data that might generate if people are willing to share that. And we have seen that with the OpenStreetMap, that people are willing to share. At least there's a certain significant amount of people that is willing to do that. Okay, maybe we are all rather tired. I'm not sure if there are discussions points from the eScience Center that we should now put on the table. If not, Niels, yeah?
No, I think I think we painted the picture of the project very nicely today. I think the next step is to concretely plan what the first step is. You already pointed some, which is nice. Maybe it's good if we actually look into what it would take to update this system, but also into the data set that Fedor mentioned, just to see how different this is technically, and update from there, I guess.
Okay, then let's conclude. Yeah, Niels?
Yeah, I also...
Other Niels? Niels, can you come to the microphone? Otherwise, get complaints from the online folk.
I vote. Yeah. So from the expert point of view, I think it would also be nice if we could maybe during the sprint or before or whatever, host a meeting where we can also present what we have to offer. To the research, like in technology, but also maybe R&D efforts we are in, etc.
Very good suggestion, and yeah, that also happened a little bit in the previous project where we had say connections with say both the developers of the systems, like Mike Horember with Oracle, and Shintaro, who's more say in the application side, how it's applied, and I think that's a very good suggestion. So probably December is very busy, but then also January. I think that is a good scheme. Yeah, to organize a session. Maybe we can do it on site again. If we know more rules then after 4 December. Otherwise, I think we should continue and have an online session showing the possibilities from the different experts in the project setup. Yeah. Thanks, Niels. Okay, with this very wise suggestion, I think it is a good moment to close the kickoff. I would like to thank you really very much. I also look in the camera again, it's a bit clumsy to stand here, not seeing my computer so well. Thanks all for taking the time, especially if you are behind the screen, but also if you're in the room. I realize it's a long sit. And I hope that the next meetings we can be a bit more interactive and really discuss more together and work more together. Okay, for now, I wish you all good evening. Michiel, good evening. You're still listening. I was just checking if you were there because we see the drinks at the other side. So maybe we check if they're what happens. Okay, you didn't hear that. Good evening, everybody. Bye-bye. I close the session. Bye.